Hello and welcome again to my lecture series on stability of compact minimal submanifolds. So this second part of the series is devoted to show examples of stable and unstable compact minimal submanifolds, mainly in the sphere. Okay, so the talk is divided in three parts. We will first see that graphs are always stable, and then we study the most easiest examples of minimal submanifolds, those that are totally geodesic. And finally, we will present another examples, which are the Clifford hypersurfaces. Okay, so what can we say about graphs? So let's consider a phi of two-sided minimal inversion of a compact manifold with normal n. We have already seen in part 1 that the Jacobi operator is actually equivalent to the Schrödinger operator given by the Laplacian plus the length of the second fundamental form plus the ambient Ricci curvature in the normal direction. Okay, so our hypersurface is stable if the first eigenvalue of this operator L, that we are going also to call it Jacobi operator, is actually non-negative. Okay, with this in mind, we've got the following result. I take a smooth function satisfying this equation, which is divergent of the gradient of f divided by square root of 1 plus the length of the gradient square equals 0. That equation is precisely the one we have to put in order the immersion phi, which is just the graph of f, to be stable, to be minimal, sorry. Then this immersion phi is always stable. Okay, as a corollary, in R3 every minimal surface is locally stable because it is locally the graph of a smooth function, satisfying that equation for being minimal. So the main ingredients of the proof are the following. Phi is two-sided because we can define this normal vector field n, which is given in the first line. So we can we can consider the Jacobi operator as an Schrödinger operator over functions over n. Okay, and now we apply the following result due to Fischer Cobry and showing in the 80s, which is an abstract result for the Schrödinger operator that says that for a Schrödinger operator, if we are able to find a positive smooth function which is in the kernel of the operator, then the index of the operator, that is the number of negative eigenvalues, is actually 0, which is exactly the same that saying that the in our setting the immersion is stable. Well, in our case, which is this positive function, which is this is actually the function u given by the scalar product of the normal and the direction in the real line. So that function is actually in the kernel of the Jacobi operator because it is what is known as Jacobi function, because it is obtained making the scalar product of a normal vector and a Killing vector field of the ambient manifold. Okay, geometrically, if we are deforming our submanifold in the direction of a Killing vector field, since the flow of a Killing field is by isometries, then we are actually not changing the volume. So it is reasonable that that functions lies in the kernel of the Jacobi operator. Okay. Okay, the first big group of examples are the totally geodesic submanifold. Now, again, I recall the notion of stability. The immersion is stable if the index form is definite non-negative for every normal section in the manifold. So now we are going to rewrite this integral using the differential one form alpha and the divergence theorem. And we get the second expression in the third equation in the slides, which is equivalent to the first one. Okay, so now if our submanifold is totally geodesic, the second term of the integrand, the length of the second of the shape operator in the direction of c is 0. And the third one is positive if we assuming that we are in our ambient manifold have non-positive sectional curvature. Then actually any totally geodesic submanifold in this kind of ambient spaces are always stable. Okay, so what happened with the ambient manifold has actually positive sectional curvature. So in the rest of this part, we will analyze those cases in the when our ambient manifold is a sphere. Okay, so now we fix our ambient manifold to be a sphere of constant sectional curvature 1, and we consider a phi a totally geodesic immersion. It is well known that this phi is actually just an equator or a Greek sphere, and the Jacobi operator is just the normal Laplacian plus the dimension of the totally geodesic great sphere times the normal vector field psi. Okay, it's just the Jacobi operator is actually just a translation of the normal Laplacian. So then we've got this result that the index of this phi of this immersion of a totally geodesic great sphere is actually the codimension, and the nullity is the product of the dimension plus 1 and the codimension. Okay, let's see how we can obtain this result. So firstly, it is reasonable or geometrically reasonable, but the equators or the great spheres in high codimension are not stable. If we think of the most simple case, which is our ambient manifold is a 2-sphere, and then we are considering as a minimal submanifold just a geodesic, which is an equator of the sphere, then we can actually deform the equator following these red arrows in the picture, so it decrease its volume. So that says that the equator cannot be stable. Okay. So what happened in higher codimension? Well, first, the normal bundle of the great sphere has always a global reference. So any normal section psi can be written in this global reference as a combination of smooth function. Second, if we use this decomposition, then the Jacobi operator is just a translation of the Laplacian in each of the direction of the global reference, and delta is the Laplacian of the sphere. Okay. Now, lambda is an eigenvalue of the Jacobi operator if and only if d plus lambda is actual eigenvalue of the Laplacian of the sphere. Okay, but the spectrum of this Laplacian for a sphere is well known. Okay, so the first two eigenvalues, which are the important ones in this case, are 0, which has multiplicity 1, and the dimension d, which has multiplicity d plus 1. Then, thanks to the above relation, we get that the first two eigenvalues of the Jacobi operator are minus d, so now we know that the immersion is actually unstable because there are negative eigenvalues of the Jacobi operator, and the multiplicity is precisely the multiplicity of 0 as eigenvalue of the Laplacian times the dimension of the normal bundle, m minus d. Okay, and 0 is the second eigenvalue with multiplicity d plus 1 times the codimension. Okay, so in the last example in this talk is going to be the Clifford hypersurfaces, which are the following ones. So I consider the product of two spheres of different dimension n and m with radii r1 and r2 in the sphere of dimension plus 1. Okay, so if we carefully choose the radii of each sphere as it is written down in the slides, then phi is actually a minimal immersion. It is actually two-sided, and the normal vector field is given by this expression in the first item of the list, and the length of the second fundamental form is constant, the sum of the dimension of the spheres I am considering, and the Ricci curvature in the direction of the normal is also constant, precisely the same value. Hence, since we are in the two-sided hypersurface case, the study of stability is reduced to the study of the Schrödinger operator, L, which in this particular case is just a translation of the Laplacian on the products. So now, what we have to we do a similar analysis as in the case of the totally geodesic submanifold. First, the spectrum of the Laplacian is known for this product of spheres, and the first eigenvalues are the following: 0 with multiplicity 1, n plus m with multiplicity n plus 2, and 2 n plus m with multiplicity n plus 1 times n plus 1. Okay, so now, since the Jacobi operator is just a translation of the Laplacian, we actually got the first three eigenvalues of L, which are minus 2 n plus n with multiplicity 1, minus n plus m with multiplicity n plus 2, and these are the only two negative eigenvalues, so their multiplicity will be the index of the immersion, and finally 0 with multiplicity the product of n plus 1 and n plus 1. Hence, we get that the index of the immersion is n plus m plus 3, and the nullity is this product. Okay, so these are the three examples that I like it to present you, and so this is the end of part 2. In the next part of the talk, I will present some classical results concerning the characterization of these examples in the sphere. Thank you.